tell me whether you are able to do it based on what you have learned till now. It's like a revision.
Yes.
Shows an aerial view of wavefronts passing from the open sea into an outer harbour. So these are plane wavefronts, and this is the wavelength. The gap between consecutive wavefronts is the wavelength. And okay, Aryan, when a wave diffracts, it bends, right? So does the speed change? No. Does the wavelength change?
No.
No. Okay, that is clear. So when speed changes, and because of that, if it bends, it is called?
What?
When a wave changes speed, and as a result it bends, we call that process as diffraction. So in this, there is no change in speed. Why is there no change in speed?
Because the medium is the same.
Because the medium is the same. And so this is not diffraction, this is mainly due to diffraction. So this much everybody is clear about. Now the question is, how do we draw these wavefronts? And you have to draw the missing wavefronts here, and then you have to draw the new wavefronts here.
So you already taught us how to do this.
Okay, so can you do it?
Yes, sir.
Do it.
Do it here. Who do it there? So you told us that a line can be thought of as a whole bunch of points, and then you have to take semicircles from that, and then you get the next line. But as soon as you reach that gap, from the sides will start curving. And you also
No, instead of giving commentary, can you do it? I will see. I'll check your work. Don't be lazy.
I don't have a list, so I looked at it.
Write it in do it in a paper. Do it fast. Okay, my question to you is, how will you decide the curvature here? How curved it will be?
So we don't know if that gap is less than the wavelength.
Why don't you know?
We can just check it's less than the wavelength.
You can see the wavelength here. It's equal.
So it's less.
It's equal or less, almost same size.
It's less than no diffraction.
So that less than the diffraction if it's equal.
What if the gap
When
is
the-
less, so if the gap length is less than the wavelength, that's a no diffraction.
You are telling exactly the wrong thing.
When the width of the gap is equal to the wavelength of the waves, that will be.
What?
When the width of the gap is equal to the wavelength of the waves, there is maximum diffraction.
And if the width is smaller than the wavelength of
There is
the
no
wave?
difference.
So there is diffraction, but
No, no,
there
there
is
is
so there is diffraction.
slight.
Compared to when it is
If
equal
the
to
width is smaller than wavelength, does the diffraction become more or less? Tell me.
less.
Wrong.
So compared to what?
If the width is smaller than the wavelength, is the diffraction more or less?
Compared to what?
It's more.
It's more of a width.
Less than the wavelength.
Okay, let us see. Okay, so this shows that you haven't understood the basic concept. What is diffraction? So listen carefully now. Okay, listen enough. I got the idea what you have understood, what you have not understood. Now let us see exactly how diffraction happens. Okay, see. Who can tell me Huygens principle of secondary wavelets? Nobody knows, right? So that's what. So I have taught that for B.Com and they understood properly diffraction. So I thought I'll do it for you also. So note this down. Please note this down. This is actually in 12th grade you will learn in wave optics, but this is the true explanation for what causes diffraction. So it will be helpful if you understand it now, so that you have no confusion about diffraction. Whatever they ask, you will be able to answer. So the concept is Huygens principle of. Please note this down. It's not there in your book, but it is required to understand diffraction at a deep level. Principle of secondary wavelets. Okay. According to it, every point.
What is wavelength?
I will tell everything. Don't worry. First write this down, then I'll explain. Every point in the wavefront is a source of new circular secondary wavelets. First write this down, I'll explain it. First write this down.
What have you written in the first one?
Every point in the wavefront, Huygens, Huygen, apostrophe S.
Written when the gap is smaller than the wavelength.
What he means is, if the gap is like atomic gap, of course there is gap even in this board, but can light pass through the board? Every atom is empty space. Like that, I'm just exaggerating. If the gap is too small, the wave cannot pass through. But if you start with the situation where this is the gap and the wavelength is also same size,
So what is
okay, it will diffract.
what is the gap is smaller than the
If the gap is become smaller than the wavelength is this much, it will all again diffract completely. Okay, I think I should do one simulation and show you first. Then we'll come back to this. Okay? Just hold on. Wait a minute. Okay. Now look at the simulation. Okay, have you copied the Huygens principle? I want to erase it.
No, sir. No, sir.
Copy it fast.
Yes, sir.
Otherwise, you can take it from the video. Done.
Yes, sir.
Done.
No.
So,
Okay. Copy it from your friends. Okay, now look here. You have waves here. You can imagine the bright blue lines to be the crests and the black lines to be the troughs. Okay. So now this is a point source, so it is producing circular wavefronts. But as the circle becomes bigger and bigger in radius, Bharat, I want your eyes and ears here. But as the waves become bigger and bigger, it appears to be like a plane wavefront. It appears like a flatter and flatter. The arc of a big circle becomes flat. So it starts to resemble plane wavefront. Agreed? Agreed till here? Now let's put an obstacle in the way.
but that's only in the case of
Any wave, if it is any wavefront is circular, if it spreads far enough, it will become part of a big circle.
the wavelength of the circular wavelength.
The wavelength is the distance between two consecutive crests or two consecutive troughs. Two consecutive blue lines or two consecutive black lines, the distance between them is wavelength.
So, what wavelength?
What is wavelength?
Length. Wavelength.
Wavelength I will come to it, wait, first understand what is the diffraction. So now you have wavelength of this size. See the size of the wavelength. This is the wavelength between two consecutive crests. So you saw the length. Now let's create an obstacle of similar size. So this is the obstacle. Now see here, the obstacle is bigger than the wavelength. Okay? If the wavelength is smaller than the obstacle, you can remember that it is similar to the light passing past the scale. Right? Remember like this, from what you know, you go to the unknown. You know that is light showing diffraction right now? Is light showing diffraction right now? You can see a very sharp shadow here of same shape as the meter scale. So is light undergoing diffraction?
So it is, but not visible enough.
Oh, if it is not visible,
No.
you say that it's not. As simple as that. If light was diffracting, it means light would have bent around the scale. If light had bent around the scale, it would have reached the shadow region. You cannot find a shadow if diffraction is happening. So the fact that you find a sharp shadow means light is traveling straight lines without bending around the scale. Enough. Focus. So that means light is not showing diffraction right
So,
now.
but if you shine a flashlight as a ruler, and then you bring the ruler very close to the source of light, not very close, but say the wall will be very far away, then it will show diffraction.
Right now I am talking about if you have very sharp edge, metal edge, very sharp, then you can see diffraction patterns, but right now you are not seeing this. The reason is this obstacle is too big compared to the wavelength of light. Are you getting it? See, right now I have two fingers, the gap between my two fingers is too huge, there is no diffraction. Because this gap is much bigger than the wavelength of light, you don't see any bending, you see clear sharp shadows. Are you getting it? So this reminds you, Tushar, please you can talk later. So this reminds you that if wavelength is smaller than the width, this is the width of gap. Okay? If the wavelength is smaller than the width of gap, then what do you see? Is the diffraction? Is the diffraction? Yes or no?
No.
No. So if wavelength is much more smaller than width, no diffraction. So the other case must be true. If wavelength is bigger than width, lot of diffraction. So you can write it as bigger than or equal to the width. If wavelength is greater than or equal to width, you will see lot of diffraction. So let us see now. I will show it to you first. First watch the simulation. Right now there is bending, but you can see here there is like a shadow region. Since the wavelength is smaller than the obstacle size, the bending is less.
So could you put the waves as
Wait. It doesn't matter. Right now it is bending till this much. Okay? Here the wavelength, the energy of the wave is very less. Now let us increase the wavelength.
So you should light down it goes like that.
I'll tell you how we suddenly shifted because these concepts are done already, but I realized that I haven't taught them in proper depth.
So question.
After I finish showing the simulation. So now to increase the wavelength, what should I do, Aradhya? What should I do to the frequency? I want to increase the wavelength.
So the frequency should be
Increase?
proportional.
So I have to increase the frequency. So here waves. Now see what happens. You see? Now there is no shadow region. The wave has affected around the obstacle and you find that the wave is present behind the obstacle also. You getting it? Now the wave has come behind also. Now if I make it even bigger, you will see the complete thing. How does it matter? Yeah, waves undergo diffraction, whether it is sound or light or ripples of water, it doesn't make any difference. They all undergo diffraction. It's only the wavelength of the wave which matters compared to the size of the obstacle. So here this is the obstacle size, the wavelength is this much. So wavelength is still smaller than the obstacle size. So if I make it equal, so let me make the obstacle smaller. Okay, now obstacle is equal to the wavelength. Agreed? Agreed everybody?
Yes, sir.
So clear it. Now you will see maximum diffraction. You see? The wave has gone past the obstacle. Now if you make the obstacle smaller than the wavelength,
So there is almost no difference in the wave.
Yes, sir.
Yes,
the wave is obviously same. I only change the obstacle size.
No, so after the
Yeah, so that means it's completely bending past the obstacle. The obstacle has no influence. See now,
the 3D view.
very 3D view doesn't add anything. Now what you are seeing is some reflected waves are also going back in all directions, that is creating the distortion in the waves. But you can see that the obstacle has no effect on the wave is just bending past the obstacle and going undisturbed. So if the obstacle is smaller than the wavelength, then the diffraction is maximum. The smaller the obstacle, lesser the effect it will have. So correct it.
Smaller
I'm
the
giving you
obstacle.
correct one. This is the correct thing.
So but now so can we look at when is the wavelength, when is the diffraction maximum, when it is written in the answer screen it is written when it is equal to the wavelength. So
That is compared to when the gap is, what do you call it? When the gap is bigger than the wavelength, Compared to that, it is maximum when the gap becomes equal to wavelength.
So,
But if the gap becomes smaller than wavelength, diffraction will become even more.
so remember that waves are refracted most when the width of the gap is similar to the wavelength of the wave.
Yes.
So,
Similar and smaller.
so smaller or similar.
Okay, wait. You don't have to take my word. I'm going to explain the concept. Then use your own brain and do whatever you
So
want.
could you do one thing? So could you make a gap?
Wait, I will show you the diffraction how it happens by
So can you
secondary.
make a gap? So could you make a gap like make two and then throw this gap in between?
Okay.
So just add line source.
Not source.
That wall first.
What is going on, sir?
So restart it.
So why the waves like bouncing off?
Reflection.
Check what
It's reflecting. So you can see it's reflecting. Okay? If the slit width is if the slit width is similar to the wavelength, it diffracts this much. Okay?
And the rest are being reflected now.
Yeah, the rest are being reflected. Okay, now what I will do is I will make the slit width smaller.
So no, so can you increase
So, but then
frequency?
You first disagree with me when I said if slit width is smaller, diffraction is more. You disagree? So let us see the proof now.
But no,
So you have to follow the correct thing, not the book. How many times do I tell you? IGCSE doesn't have a prescribed book. You have to write the correct thing. Don't keep arguing the same thing, book. Now I'm making the slit width even smaller. Do you see that? Do you see that?
Yes, sir.
Now let us see.
More than refract.
I need to.
More
You
than
can see
refract.
the diffraction has increased.
So what is happening inside?
So some gap is there, through that gap it's coming out.
So now I have its reading views.
So now I'll make the gap even smaller. Now see for yourself whether diffraction is becoming less or not.
Can you make the
The intensity is becoming less because the less energy is able to come through. See, understand what is happening. If the gap is very small, the energy of the wave which can pass through the gap is very less. Okay? So when that small energy spreads into a bigger area, okay, the amplitude of the wave will be very weak. So you can't see the wave. So that's what is happening.
So that's only happens with the point, right?
Yeah, so if the gap is now slightly bigger, so that some decent energy can pass through,
then the intensity in the refraction increases if the gap is small.
listen, the intensity of the amount of diffraction is maximum only. Once
So
it
intensity and also intensity.
intensity is depending on the energy available. Energy is passing through.
So
if the gap
You
is
see for yourself and come to a decision, right?
so
Right? I'm showing all the distances.
So
You
when
see
you
for
say one thing,
yourself,
so
really. Now the gap is equal to wavelength, agreed? Now the gap is almost equal to wavelength. Now see what happens.
So we have to do that.
So diffraction is somewhat lesser now. See, actually, see, diffraction happens all around the edge. Only thing is the intensity of the wave energy decreases as you flow towards the edge. Listen carefully to what I'm saying.
sir, I
Listen carefully. Wave is bending everywhere. All the time the wave is bending. But the energy is maximum in this region, and in this region the energy falls off. So if energy falls off, the amplitude falls off. If amplitude falls off, you don't see the wave. You getting it?
Yes, sir.
So there is some wave present here also, but the energy carried by that is very less. Now let's understand that in detail. I want you to hold on for 5-10 minutes. Let me show you how to draw the new wavefront using secondary wavelets.
It's a
Then
small question, sir.
your questions will be answered automatically. Wait.
This is a small doubt. So you can answer like with a yes or no. until the gap is equal to the wavelength. Then at that point of time, it's a variation in diffraction. But then after the gap becomes smaller than the wavelength, then it becomes a question of intensity of the
Yes.
wave, where diffraction remains the same. Also.
Yes. Yes, that's what I'm saying. So you will see it when we draw a new wavefront using secondary wavelet principle. So that's why I want you to understand it properly.
So, but if the gap equals the wavelength, shouldn't the diffraction be maximum?
Let me do this question, you will understand everything. See here. So suppose this is a plane wavefront. Okay. Suppose this is a plane wavefront. Aryan, please. So if this is a plane wavefront which is traveling in this direction, when I ask you to draw a new wavefront and I say that wavelength is this much distance, what do? You measure this distance in front and draw a parallel line. That's what you do? Agreed? But how does the wave create a new parallel wavefront? What exactly is happening? And why does the wave bend around obstacles? If you want to explain that, okay? The answer is every point in this wavefront behaves like a source of new circular wavefronts. So let me explain. So you can imagine every wavefront be made up of millions of points, and each of these points is a source of new circular wavefronts. That means from here a new circular wave is emitted. From this point a new circular wave is emitted, and they all travel with the same speed as this wave, as the original wave. So after every one time period, from each point if a circular wave has emitted, it will travel a radius of one wavelength. Agreed? So if you draw it, see what happens. So you will use a compass, I will use this contraption.
So,
Wait, let me finish for 5 minutes, then I will take a question. So this is the wavelength, agreed? So now from this point the secondary wavelength has been emitted. From this point also. From this point also. From this point also. From this point also. Like this, if you keep drawing the secondary wavelets, the outer envelope of all these secondary wavelets becomes your new wavefront. Please do it in your notebook. What? What? Now if this one is a plane wavefront traveling till infinity, extending till infinity, then the next one will also be extending till infinity, a straight line. So this is the outer envelope. Agreed? So the reason it is curving here is because I stopped drawing. If I extend this even more and again draw, again it will also extend. This one will also extend.
So that means the quality of any wave is to curl.
Yes. Yes.
So if you
Yes.
even let a straight wave go like in empty water for a kilometer, then eventually the wave will curl.
Yes. So now let us see the effect of.
So you take the distance.
Wait a minute, please. Let me explain everything. Then I will take a question. You are just wasting time. I have just shown you how to draw the new wavefront from the previous wavefront. Now let us see the effect of gap size related to the wavelength. What is that? How it affects?
the more it is equal to the wavelength of the wave, the greater the diffraction.
Wait. Now here you can see the difference. Here the gap size is small compared to wavelength. Here the gap size is large compared to wavelength. So when the gap size is large compared to wavelength, if I did the same thing, so see here, this is the wavelength. This is the wavelength, right? So if I draw from here, from this point, like this. Are you getting it? So the outer envelope of all these secondary wavelets will give me this shape. But why do you think they have not drawn this part?
Because that does not have enough amplitude to be seen properly.
Exactly. So there is wave present here also, but the energy carried by this part is very less. Now you need to understand why is that happening. You know the answer?
I can try.
Right.
So because the place where the line is created, it's combined because there's so many points on the wavefront around the wave core, and using those circular wavelets, a lot of points create.
No, there is a more direct, simpler answer.
So they
See
get
here.
overlapping waves.
No
which increase
need to
amplitude.
think about overlapping now. See, it's very simple.
So
Look here, from here to here, whatever energy was carried by the wave is 100%. Right? From here to here, the entire wave of the energy of the wave is passing through the gap. Now that entire 100% energy is distributed over this region. Agreed? Now, most of the energy which was carried here will come straight like this. Agreed? That energy has not spread out in any way. If the energy is going to spread into a bigger area, then it will get diffused, dilute, etc. Energy density will go down. But here, whatever is there, it has just come straight in front. So, in the same concentrated form, the energy has come here. So, what is present here is the one which is spread out. So, the energy which was present here, the small fraction of energy, that has spread into this region. Are you getting it? The energy which was here, that has spread into this region by diffraction. And the small amount of energy which was present here, that has spread into this region by diffraction. Whereas the energy which was present here has come straight without, it's like this, you take a spoon of jam. If you carry the same spoon of jam here, it will be same sweetness. But if that one small little bit of the jam, if you spread over a bigger area, apply it uniformly over a plate and then lick the plate, it will not be as sweet. It's spread out, it's diluted.
So for the straight line on the wave, the energy transfer is from point to point. So that's
Yes.
the energy remains diluted.
Yes, the same energy is coming here.
On the edges.
But the edges, now whatever diluted energy is here, that is contributing, that is spreading out and forming secondary wavelets and giving rise to this. Are you getting it?
Yes.
So that's why this area of invisible region where there is no wave shown, it is basically the energy is so less that you can't see it. Last two rows are sleeping. Please wake up. Wake them up. Do you understand now? So by secondary wavelet principle, from this point, if I draw the secondary wavelet, I will have a wave which is present, no doubt. So if this is the wavelength, from here I can draw.
So but the why they even drawn those little curves, so they could have just moved them.
No, those little curves are present.
So rather than
So they are present to show that the wave is spreading out.
Yeah. So see, from here if you do, you will get till here, right? And then from this you will get till here. From this you will get till here. You getting it? This energy is already weak. So from that whatever you get a new secondary wave, it will be even weaker. If it is spreading out into a bigger one. So they are all neglected. So you can say that the amount of you can start neglecting from this region like that. Yes.
So can I show you more?
Yeah.
So you said that these things aren't really distinct because the amount of energy in this particle has to be transferred to these many particles
Yes.
on this length.
Yes.
But then why has even this part been shown? Because if this particle has been transferred and energy equally among this area, then why would it prefer to give it to this and not to this? And like, what's the point of doing that?
No, see, this resultant wave here, this, let me erase it. wavelength is not only due to this. It can also be due to this. See this wavelength. Even from here you get. Even from here you get. Even from here you get. So it's getting contribution from all the neighboring points. So the further you go, the weaker the contribution from the main part of the wave. So that's why here on, from this side onwards you see that the energy starts to fall. So you just take a limit till where you can see the energy passing.
So according to this rule then, so if you in the simulation...
One second. This question I will take after we draw this. Just be patient. So now you saw that if the width of the slit is very big compared to wavelength, in front of the width you continue to receive the plane wavefronts itself, the plane parallel wavefronts. Tushar, wake up. Okay. See, you had a plane wavefront, in front also you have plane wavefront. If the width is large. So when the plane wavefront continues without any curvature being added, we say the diffraction is less. But now you see what happens. If for a small width also, if diffraction was not happening, you should continue to receive the same plane wavefront. So if I draw like this, if there was no diffraction, I should continue to receive the same wavelength plane wavefronts. Like this. If I had got wavefronts like this, it means no diffraction is happening. But let us see what actually happens. So how will you know what actually happens? Use the Huygens principle of secondary wavelengths. Measure the wavelength and then make points. Now draw. Then till this edge. So now the outer envelope is this. Are you getting it? Then the next wavefront would be from here you have to draw. Make these dots and then.
So why don't we measure the new wavefront or the new
What?
So why do we measure the new? Why do we use the new distance between the obstacles instead of?
I am not getting you. What are you asking? Wait, let me finish. Let me finish this one then. So the new wavefront is like this.
Yes.
The next one will be like this. So you can see that instead of a plane wavefront, it has become a circular wavefront. So when the gap is smaller than the wavelength, it becomes a circular wavelength. If it is equal also, it becomes circular wavefront.
So basically then it becomes a
circular wavefront. So diffraction is maximum the moment the gap size becomes comparable to the wavelength.
So how did you take these? So
The gap is, see this plane wavefront would have come and formed here, right? So every point in the wavefront is a source of circular secondary wavelets. That is Huygens
but
principle.
how do we take every gap?
यहाँ पे gap है, yeah, here also rays are there, but they can't travel through the obstacle, no? Yeah, so it is made up of continuous points. So the closer the points, the more accurate your wavefront will be.
Then we keep on trying.
The outer envelope of these secondary circular wavefronts wavelets is the new wavefront. Outer envelope, like this, like this, like this, like this, like this. So this outer